Welcome to the afternoon session 4A, undergraduate collaborations. I thought I'd take advantage of my time to say a little bit about my experiences with Alex. My name's Jim Babb. I joined as the first postdoc at ITAMP and joined the group that consisted of Mung Lee Du, Bernard Zeigelman, Steve Lepp, Atul Pradhan, Ron Friedman, Brendan McLaughlin, George Victor, and Kate at the time. And even though Alex was very busy at the time and perhaps soon to be busier, I think, taking on the ITAMP responsibilities, I benefited from his door always being open, even late at night. I came with some mutual interests in long-range forces, which I had picked up with my thesis advisor, Larry Spruck, but rapidly found myself drawn into molecules with Alex. I didn't cut my teeth the same way maybe many of you did, which is on radiative association. In fact, I'm not going to talk about radiative association because at a symposium in honor of Alex, with Alex present, 50% of the world's expertise is here, and that's not counting the rest of us. So I thought I would talk about another molecule that we worked on, which was the hydrogen molecular ion. And Gordon Drake had talked a little bit about some of the progress. I want to talk about a different aspect, which is the hyperfine structure of the hydrogen molecular ion, which I got into through Alex's introduction. And this will be just a very fast presentation. I don't know if you could even call it a talk, as a skim or something. The hyperfine structure H2+ is a lot different than the hydrogen atom, which Bernard Zeigelman talked about a little bit. I'll talk a little bit about that, some measurements in H2+, calculations, and the deuterium molecular ion. There's been a lot of progress in work on H2+ precision work. Gordon talked about some of the aspects. Things started out really in the Born-Oppenheimer picture, which Alex had worked on with Bates and others, and rapidly progressed to adiabatic approaches, which he had worked on with McCarroll, non-adiabatic approaches, and even now in the modern era, there's work on full variational approaches, such as was talked about by Gordon, work by Yan, Zhongchao Yan, Gordon Drake, Korobov, and others. But even still, things go on. There's relativistic approaches using the Dirac equation, bright Pauli approximation approaches, which are also good for relativity, and are accurate to order alpha squared, Rydberg, and even further need for radiative corrections, which are being looked at as we speak in higher terms. The hyperfine interaction H2+ is a fundamental interest and has been studied over many decades. And it's very similar to the hydrogen molecule. However, there's a fundamental difference, which is H2 is diamagnetic, while H2+ is paramagnetic. And that will have some implications for precision work, as we'll see. As Bernard showed, in the hydrogen atom, there's a very precise experimental value obtained with the maser, the CFA, for the hyperfine transition frequency. The theoretical status is not as good, but it's still pretty precise. You can do pretty well, as Bernard mentioned, with the Fermi contact interaction, and then even better if you include a naive correction, which is the reduced mass effect between the proton and the electron. And just including this factor, which is called kappa in the business, brings you down to 1420.486. So you're only 80 kilohertz away from experiment. And then QED and hadronic corrections and things, which are challenging and are done by people like Saperstein and Pachuki and others, can bring you down to this best theory value, which is down to 2 kilohertz uncertainty. The situation for H2+ is a lot worse, but there is some experimental data, nothing like the maser results for hydrogen. Particularly the Demelk group in the 60s obtained some energy levels at the 3 kilohertz level, accuracies in an RF Paul trap. But this was for excited vibrational states in H2+. Later, the Carrington group, which I don't think is continuing these experiments, had done some highly excited vibrational states. And then there was an interesting experiment done by Lundin and collaborators where they looked at the Rydberg hydrogen molecule. That's an H2 plus with an electron in a high orbit. And they can unravel all this complicated structure and obtain a value for the hyperfine structure. Gordon had mentioned the polarizability. This is a different experiment. They had obtained a hyperfine structure for H2 plus. Fortunately, there's a recent effort by this group, Osterwalder et al., including Jungen, who did a similar measurement in the Rydberg hydrogen molecule. So there is another group looking at this problem, and they're about 10 times less accurate than Lundin claimed. So that's some recent activity on the hydrogen front. In the theory side, Alex, with Patterson and Somerville, solved the Dirac equation for the hydrogen molecular ion and obtained the hyperfine Hamiltonian in a analytical form. Experimentally, it had been used in a phenomenological form. That is, you identify the couplings between the different spins and then fit the constants. And Alex's work had come before that, actually, building on the work Frosch and Foley had done for the diamagnetic case. But this important paper really laid the groundwork for theoretical studies ab initio. And later, Alex and I looked at this mass effect in H2+, the analog of that kappa term. In the usual Born-Oppenheimer approximation, the nuclei move in the field generated by the electrons. In that picture, we looked at the back action, going beyond that, of the motion of the nuclei on that electron wave function. And this is building on work that Callahan had done with Alex in the 70s. Interesting new development is that Korobov has revisited this calculation and used the variational approach that Gordon mentioned. He actually gets good agreement with our earlier perturbation theory approach. So even though we had to wait almost 15 years, it's nice to have independent confirmation. There are still remaining discrepancies having to do with spin flip transitions, and I think Vladimir is looking at those. So why not HD+? Why not look for the deuteron quadrupole moment? This is a problem that has come up now and then in this study. And it has been calculated now by Korobov and collaborators. They find it's about a 10 kilohertz effect. And there's some new experiments that are being done, which is other good news on the H2+ front, by Schiller's group, and which Gordon showed some of the transition frequencies. And they can't get to this precision, this 10 kilohertz yet. So why not D2+ to look for the deuteron quadrupole moment? Maybe. There's actually an experiment by that same collaboration, Osterwalder, where they looked at, just recently, the D2+ hyperfine structure. It's the first determination that I know of the D2+ hyperfine structure from Rydberg D2. And so it's a comparison between our results and theirs that can be performed. Also, interestingly, Aveen mentioned H2D+, and there's also D2H+. These are being measured experimentally, too, in an exciting development by a group in Kuhn, where they get an experimental precision of 20 kilohertz. That's way ahead of theory. Even the agreement's better than Aveen mentioned for the transitions she was talking about, but still it's quite far away. Nevertheless, this is at the level where you might be able to see a deuteron quadrupole moment effect in H2D+. So that's an exciting potential development. And in the future, there'll be sympathetic cooling, sympathetic molecular ion cooling. So I'm looking forward to a resurgence again in interest in this high precision, hyperfine structure. And with that, I'll turn myself over to questions and conclude my talk. Thank you. Any questions?